All right, let's go ahead and start in on this. For the people who come in later, I'll let them in. So I'm recording this. I'll put it up online later. What do we want to start with?
I have 4 questions on the multiple choice.
Okay, let's go multiple choice then.
The first one is number 25.
25.
And
Okay.
I was just wondering, like, how did you know that trial 4 didn't fit in with the other data?
So absorbance and concentration data should be nice and consistent. And so if we look at our concentration data, we can see that each of these jumps are not totally consistent. Let's see. So there's a 0.5, there's a 0.5. That's only a 0.025. But we could, if you find the ratio of these numbers to each other, we should have some consistency here. And number 4 doesn't have that same ratio. So normally, where's my pen? Normally concentration and absorbance data should give us a nice straight graph with a, well, not a straight graph, a straight sloped line on a graph. So if absorbance is on this one and concentration is on this side, we should get a line with a constant slope, which means that, you know, the ratio of absorbance over time or over concentration should be the same number for each one of these. And if we do that, this guy sticks out and it doesn't work out.
Okay, and then number 26, I wasn't sure between the answer choices C and A.
C and A, beta carotene, 250 and 320s due to transitions, and between 380. All right, I'm hoping that the answer is actually C, right?
Yeah.
Okay, so this is a question dealing with the different types of electromagnetic radiation and how they affect molecules. And so you're just going to have to memorize the fact that microwaves cause rotations. Not UV. Infrared causes vibrations, and visible and UV cause electrons to jump energy levels, or they call it electron transitions. And so these are all, it says that the diagram above shows the ultraviolet spectrum of beta carotene. So these are all ultraviolet wavelengths. So they should all cause electron transitions and nothing else.
But doesn't A and C both talk about the transitions between the energy levels?
This one says vibrations.
Oh, okay. I didn't notice that.
Yeah.
And then on number 29, I thought the answer was A. But...
Ooh, of course, mine's all fuzzy. To determine the number of moles of copper in the sample, student measures the absorbance of known concentrations. A cuvette fills some solution. Data recorded on the basis of the data provided, which of the following is possible error. I'm going to have to open up a different file so I can actually read this. Not that one. Unit 4. Come on. La 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 la. 26. 29. All right, so if we look at the data here, this is what I couldn't see on the other screen. As I go up for each of these known concentrations of copper, I'm increasing my copper ion concentration, but my absorbance is not consistently going up. And so I should have that consistent correlation between the concentration and the absorbance. So something funky is happening. My guess is with this 0.1 concentration one, because this should be somewhere between 0.23 and 0.46.
Yeah, the answer is C, and it makes sense. I just didn't know like why it couldn't be A either. Like, couldn't A be some kind of possibility?
It's so it could cause the same problem, but usually what happens, and unfortunately we did this lab today in class and you missed out on it, is that you have a higher concentration and then you take that higher concentration and you dilute it down, and then you take this concentration and you dilute it, and then you take this concentration and dilute it. It's called a serial dilution. So it'd be very difficult to take a sample that was diluted wrong and then get any decent data at the lower concentrations from that. I do think that's sort of a poopy question. Just because, I mean, it could have been a dilution problem if you didn't think about it going in order. And they don't,
that makes sense. Yeah.
Yeah, they don't specifically say in the question that, you know, they did a serial dilution, which would help us know more what was going on.
And then my last question is for number 39.
39, okay.
I said originally the answer was B.
Yep.
So yeah.
So this is a sneaky question. If I want to get solid potassium nitrate, but it's in an aqueous solution, that means that potassium nitrate is dissolved in that water and it's currently broken up into ions. So there's nothing solid sitting in that aqueous solution. So if I filter it, everything is going to pass through the filter paper. I'm not going to catch anything. Since potassium nitrate is soluble in water, which means I'm going to have to get rid of that water to reform solid potassium nitrate. So we'd want to evaporate it. Now, if they were talking about some other chemical other than potassium nitrate, something that wasn't soluble, like if they talked about silver chloride, that's not on our SNAP rules, and so we wouldn't necessarily know that whether that would be. We would assume that that's not soluble. Then we could totally filter it and collect that solid.
Okay, thank you for answering my questions.
Welcome. Since we're here, anybody else have multiple choice questions?
Number 34.
Yes, Ms. Brooklyn, 34. When 70 milliliters of a 3 molar sodium carbonate is added to 30 milliliters. Okay. I'm going to switch back to this guy so I can draw on it. So this is also a sneaky question. So we're not talking about diluting solutions like we usually do when we're talking about concentration. We're talking about actually mixing two solutions together that both have sodium ion in it. So if I look at this first solution, I got 70 milliliters of a 3 molar solution. So if I have 3 molar and I've got 70 milliliters of it, that means that I've got, so 3 times 0.07 gives me 21 moles of the sodium carbonate. Now in that 0.21 moles of sodium carbonate, I have 2 moles of sodium ions. So I could say that in 1 mole of sodium carbonate, I have 2 moles of sodium. So just from this solution, I've got 0.42 moles of sodium. And then I can do the same thing for this solution. I've got 1 molar of sodium hydrogen carbonate, and I've got 30 milliliters, which is 0.030 liters. Yeah, that's a decimal point. Multiply that up from this solution, I've got 0.03 moles of sodium hydrogen carbonate. In 1 mole of that sodium hydrogen carbonate, I only have 1 mole of sodium ions. So that means I also have that many moles of sodium ion. I'm going to add those two together. So 0.42 plus 0.03, it gives me 0.45 moles of sodium ions. And that's in a total volume of 70 plus 30 is 100 milliliters. So 0.1 liter. So that gives me that 0.45 molar. You got to be really careful whether they're asking you about concentrations of a specific chemical or whether they're talking about concentrations of a specific ion.
Okay, thank you.
Welcome.
Can you please go over question 19?
19. All right. I wouldn't worry so much about 19. This slipped past me. These graphs aren't on the AP exam anymore. Nor is really talking about saturated solutions. So don't worry about this guy.
Awesome, thanks.
Anything else on the multiple choice? I'm going to take your silence as a no.
Actually, I have one.
All right, go for it.
Number 25.
25. Oh, we talked about this one before you logged on.
Oh, okay, then I'll just watch it.
Okay. It's all about the pattern of the absorbance versus the concentration.
Oh, okay. That's fine. Thank you.
Yep.
Can you go over question 5, please?
5. Yeah. Okay. So question 5 is talking about ratios, basically, is what I was talking about. And so we have to be able to figure out what those ratios are based on what the pictures are showing us. So in this first beaker, we've got silver nitrate. We've got 1 silver ion for every nitrate ion. In the second beaker, we've got magnesium chloride. So we've got 2 chlorine ions for every magnesium. In this final beaker, they tell us that we've got this big old chunk of solid silver chloride sitting at the bottom of the beaker. And then we've also got, we can look at the ions floating around the solution and see what's there. So we've got these symbols that look like this, that look like those magnesiums. And then we've got these symbols that look like the nitrates. So all that's left in this solution is the magnesium nitrate. I don't see any silvers floating around. I don't see any chlorides floating around, which means that when these reacted, I didn't have any excess of one chemical versus the other. I had just the right amount of each chemical to mix together and make this perfectly happen. So if I think about how these would combine, I can think about the balanced chemical equation. So if I've got silver nitrate reacting with magnesium chloride, I know it's making AgCl and magnesium nitrate. If I balance that, I gotta put a 2 there and put a 2 there. So what this is telling me is that I need 2 parts of silver to react with 1 part of magnesium chloride to make 2 parts of silver chloride and 1 part of magnesium. So I have this 2-to-1 ratio for my reactants. So if I look down at my choices, A and B are out because those show basically 1-to-1 ratios of my reactants. And so that would make one of those be an excess reactant and one of them be limiting. That's not what I want. So I can narrow it down between C and D. So if I have 2 molar of silver nitrate, and it tells me that I have 1 liter solutions of each of these guys. When I mix those together, if this is a 1 liter container and this is a 1 liter container, when I mix those together, I'm going to end up with a 2 liter solution in the end. So if I have 2 parts of silver nitrate reacting with 1 part of magnesium chloride, they already said I don't really care how much silver chloride I make, but that's going to make 1 part of magnesium nitrate. But that's going to be out of twice the volume. So it's not going to be 1 part of magnesium nitrate, it's going to be half a part of magnesium nitrate. So that gets me to D, where I've got that 0.5 molar of the magnesium nitrate.
Thank you.
You're welcome. Since we're here, I think we talked about this in class already, but I told a lot of people, don't worry about number 7 for right now. There's some obvious, some sort of big piece of information that's missing from that question. So don't worry about that one. Anything else on the multiple choice?
I don't have a multiple choice question, but I have a question in general.
Fantastic, go for it.
Okay, so like, what is a wavelength setting? Because like, I understand like it's the highest peak on the like absorbance graph, but like, what is it?
So let me see if I can find it. I think there's one on here. La, 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 la. I can use that one. I just went by if I need to. Yeah. So basically what you could do is if we had a substance and we didn't know what wavelengths it absorbed the best and which ones it transmitted the best, we could take a colorimeter or a spectrophotometer like the one we used in lab, and we could set it to different wavelengths and measure the absorbances at those different wavelengths. So if we had this picture, this isn't a fantastic example because these aren't visible wavelengths, but the same idea would work. So we'd measure it at 20, at 200, we measure at 220, at 240, 260, 280, and 300, and then 320, 340, 360, 380, 400. We measure it at several different wavelengths along. And wherever the highest peak is, that is the wavelength that that substance absorbs the best at. What that means is that whatever that wavelength is, that's the wavelength we want to set our spectrophotometer or our colorimeter to when we do those Beer's law tests like we did in lab today. So in lab, we measured at the orange absorbance. because that's the color that that's the color wavelength that the copper solution absorbs the best. So we're going to get the biggest sort of spread of numbers. It's going to be easiest to read those numbers.
Okay, thank you.
Welcome.
Can I just ask, why does absorbance matter? Like, what's it used for?
So for our purposes in chemistry, absorbance is used to help us talk about concentration, because we know that absorbance and concentration are directly proportional to each other. So if we can measure something that is a known concentration and know its absorbance, which is what we did in lab, right, when we made the different dilutions, then if we have a solution that has the same chemical in it, but we don't know its concentration, we can then identify, based on its absorbance, what that concentration would be.
Okay, thank you.
Yep. Any other sort of in general topics or questions that you've got?
Can we go on
Yeah, oh.
mastering?
Oh.
Sorry, who was
Sorry.
you can go first.
Okay, thank you. So just in general, when you're comparing like different compounds and then it asks for which one is most soluble or which one's least soluble, what are you looking for?
In general, you're looking for information about their polarity and what types of intermolecular forces they can form. So we talked about the idea that likes dissolve likes. So that was, where was that? It was like 4.2 in your packet, I think. No, obviously not. 4.3. 4.3. So we have this idea that like dissolves like. So the degree of polarity matters. So something that is more polar is going to be more likely to dissolve in something else that is also polar. Or something that is more non-polar is more likely to dissolve in something else that is also non-polar. There was a question on your quiz this week or last Friday that had I don't remember the exact chemical, but that there was C2H5OH and like C10H something ridiculous. And it was asking, and there were some other choices too. It was asking which one was going to dissolve best in water. So since we have water, we know water is polar and it can hydrogen bond, which means it is going to dissolve other things very well that are also polar and or can make hydrogen bonds. So anything on our list that would be non-polar, like CH4, is not going to dissolve the best in water. Both these two top chemicals have this OH on the end, which means that they can do the hydrogen bonding like water can. So these would both be decent choices to sort of narrow this down to. The only difference between these two chemicals is this carbon chain gunk stuck onto the end of this hydroxide, onto the end of this OH. In this case, this would be the best chemical that would dissolve in water. Having a shorter carbon chain on the end means that there's less mass, there's less stuff on that molecule that's not doing that hydrogen bonding with the water. On this molecule with a long 10 carbon chain, that's a long, decent, high percentage of that molecule that cannot make the hydrogen bonds with the water. So if more molecules by mass can hydrogen bond with that water, then they're more likely to dissolve in that water.
Okay, thank you.
Yep.
My question kind of went with that, but
Okay.
it's on mastering chem and it's number 4.
Ooh, okay. Let's see. I feel like I can't sing the Jeopardy song anymore. Like we need time to mourn Alex Trebek before we can sing the Jeopardy song again. All right, number 4, you said?
Yes.
Okay. Cool.
Oh, like I don't know how to tell if it's more polar or less polar.
Okay. So if we're looking for least soluble in hexane, if we look at this molecule, pretty much anything that's going to have just carbons and hydrogens in it like this is going to be nonpolar. Because what it's going to look like, sorry, I keep flipping back and forth. But it's just going to be carbon with hydrogens on it, and then another carbon with hydrogens on it, and another carbon with hydrogens on it, and just keep going for however many carbons it's got. So this compound, hexane, our solvent, is going to be very non-polar. And so if I look at these other choices, butane also is just that carbon-hydrogen chain. So that is also going to be very non-polar. Butane would love to mix with hexane, but we're looking for the one that's least soluble. So butane is off our list. Let's see. So chloroform is a carbon in the middle with 3 chlorines around it and a hydrogen. So that one is polar. So that's on my list. Methanol is also going to be polar if I draw out the structure. So a lot of this, you have to think about the Lewis dot structures for these. Methanol is going to be even more polar than chloroform because it can form that hydrogen bonding on the end. It's got that oxygen or the hydrogen bonding onto a nitrogen, an oxygen, or a fluorine. Same thing with acetonitrile. It also is going to be polar because it's not totally symmetrical. But that hydrogen bonding is really going to affect this methanol. So since hydrogen bonding is basically as far away as you can get from the London dispersion forces that happen in those nonpolar molecules, methanol would be the least likely to dissolve in hexane.
And then I didn't understand number 9 either.
All right, so this is a dilution question. People struggle with these a lot of times. So what this question is saying is, I have I have 134 milliliters of a solution that has a concentration of 8.2 molar. And I can take that solution and dilute it down to a different concentration. And that new concentration, I want there to be able to be 4.21 grams of copper chloride in 51 milliliters of that solution. So this is going to require a lot of math. So if I have, where'd my mouse go? 4.21 grams of copper chloride. So I can figure out how many moles that is. La, 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 la. So chlorine is 35.45 times 2. Copper is, I really need a periodic table on my desk. Instead, I'll just pull it up on my phone. Come on. Copper is, I want to say, is it 55.85? No, 63.55. So its molar mass is 134.45 grams. So I know that I've got 0.0313 moles. I want that many moles of copper in, what does it say, 51 milliliters, something like that.
51.5.
The numbers might be different on the different versions. Like mine says 51. So 0.051 liters. So my final solution, I want to have a molarity of 0.614. I want that molarity. So I need to dilute down this 8.2 molar solution so that I make it have a molarity of 0.614. So I have 0.134 liters of this. Why can I not remember these numbers? 8.20 molar solution, and I want to turn that into a 0.614 molar solution. I want to know what volume I have to reduce that down to. I reduce it, what volume I have to increase it to make that happen. So 8.2 divided by 0.614. So I need that solution to have a volume of 1.79 liters. So the 1.79 liters would be the same thing as 1,790 milliliters.
Can you just keep it as milliliters instead of turning it to liters and then turning it
Yep.
back to milliliters?
You could in the M1V1 part. So you could keep this as milliliters, that would be fine, and then your answer would come out in milliliters. This has to be turned into liters for molarity.
Okay, thank you.
Welcome.
I had a question about number 11 because like on the thing where you have to sort like the solute or like the solute solvent thing, I don't know if that was number 11, but whichever one that was where you had to sort them, I got like a 0% and I had no clue how to do that.
Why did I close it? Silly. Let's see if we can find that question.
I'm pretty sure it was on number 11, but I'm not sure.
It just really started raining. This guy?
Yes.
Okay. All right, so we're talking about the different, this is a tricky thing to think about. We're talking about all of the different ways that these molecules are interacting with each other and with themselves when we're dissolving an ionic thing in water. So we've got solvent-solvent which in this case, our solvent is water. We've got solute, solute. Solute is a thing being dissolved. So in this case, that is the sodium chloride. And then we've got solute, solvent interactions, which is how the water and that sodium chloride are interacting with each other. And so if we have solvent-solvent interactions, that would be between the water molecules themselves. And then this one says dipole-dipole attractions. Because sodium chloride doesn't have dipole-dipole attractions, it's ionic. So it doesn't have dipoles. So water is the only thing that would be able to have a dipole interacting with another dipole. So that solute-solute interactions in the sodium chloride, that's where we get the ion-ion attractions between the ions of sodium chloride. And then the solute-solvent interactions are going to be forming between the water and those ions. So we've got between the chloride ion and the hydrogens of the water, and then between the sodium ion and the oxygen atoms of the water. So there's all kinds of different interactions going on there. And so when sodium chloride actually dissolves, we're taking these solvent-solvent interactions and these solute-solute interactions, and we're breaking those apart and forming connections between the water and the ions, so between the solvent and the solute. That's a tricky one.
Can we go to free response?
We can look at free response. Let's see. Somebody already pointed out a mistake to me. Natalie pointed out a mistake in class with one of the free response questions because it makes no sense. Let's see. Free response. I don't want to open up the test. I want to open up the answers. Okay. So number 1, part A has issues. So you cannot worry about that one. But what other parts do you want, Alex?
For number 12, just part A.
Well, yes.
I had no clue what to do for that.
All right. So, so this is pretty much exactly what we did in lab. So we generated a graph, just like these people generated a graph of known concentrations versus absorbance. So then we have a solution that of unknown concentration that has an absorbance of 0.35. So on my graph, I can find where 0.35 should be. It should be right around here. I can follow that across to my graph and follow it down to what concentration that should match up with. So it should be somewhere less or right around, I would say 5.5.
Okay. Yeah, I just overthought that.
So there's one of the things about these questions is about all AP questions, but especially in this section, is that there's going to be a lot of language going on. You're going to have to dig through this a lot to figure out what numbers go with what and what solution they're talking about, because there's going to be a ton of solutions. This solution has this concentration, and this solution has this concentration, and this solution is an unknown concentration. So you're going to have to, maybe make yourself some notes or doodle on your question to sort of follow along with what they're talking about.
Okay. Can we also go to number 10 for part D? The only thing that I was confused about, so scroll down a little bit more, please. So it uses the 0.00148 moles of H2, and I didn't know why.
Okay, so in this equation, we found the number of moles of magnesium at the beginning in part A. But in part D, we're talking about hydrogen gas H2. So all of the information in this PUVNERT needs to be about H2. So I need to figure out how many moles of H2 I have to be able to find that volume. So if I know how many moles of Mg I had, I can see that that's a 1-to-1 ratio with the hydrogen.
Okay.
So it would have the same number of moles of H2 gas.
Do part E for number 10 also.
Part E. So we need to make a 2 molar solution, but we only have 12.3 around, so we're going to have to do a dilution. So we'd have to do a little bit of math first to figure out what volume of final solution we would actually need. So if I need to make a 2 molar solution, which is what they're saying here, and I need 50 milliliters of that, that means that I need 0.1 moles of HCl. If that's coming from the 12.3 molar solution, and I only need 0.1 moles of it, that means I only need 8.1 milliliters of that concentrated solution. This was, if you remember way back when we first started talking about molarity, we talked about how many different methods of doing this math there were. So this is one way of doing it. You could also do this as an, let me doodle on here. You could do this as an M1V1 equals M2V2, where like 12.3 is my M1, my V1, I don't know. My M2 would be the 2 molar solution I want to make, and the 50 milliliters would be my V2. And so you're trying to find V1. You could also do this using, instead of using like a conversion factors, you could use the molarity equation. So like I know I need 2 molar solution. I only need 50 milliliters of it. Find how many moles that is.
Okay, thank you.
Yep.
And for question 6 on the free response, and then part C,
6C. Okay.
what is it talking about with the interference?
Okay. So this is, Morgan, this is kind of what you were talking about before. So here's that sort of across wavelengths graph showing what wavelengths each of these elements absorbs best at. So we can see that copper maxes out its absorbance around 500 nanometers. Copper maxes out somewhere around 800, maybe 750. 800 is sort of out of visible. So if we want to pick something between 400 and 700, where we're really only going to be able to see that copper and not the cobalt. If I can go from 400 to 700, I want to avoid that overlap from the cobalt. So I want to go in this range where it's mainly the copper ion. So I'd want to probably be in this, this range of wavelengths where that interference from that cobalt is less as much as it possibly can. So cobalt is going to be absorbing it less, and copper is going to be the only substance really they're absorbing.
And then on on the question 7, I wasn't sure how to write the equation for part A.
So this is going back to do net ionic equations. So basically anything that says aqueous is going to split up into ions. Sorry, I'm misreading. So when we've got aqueous acetic acid reacting with aqueous sodium hydroxide. So again, these are aqueous This is going to be a double replacement reaction. I wouldn't worry a ton about this first part. We'll talk a lot more about this one when we talk about acid-base reactions at the very beginning of second semester, because that's what this first thing is about.
Thank you.
Yep.
This is another like in general question, but will we need to like memorize Beer's law for like the test?
It's on your equation sheet.
It is?
Yes. It's not where the wavelength and frequency ones are. It's on the other side. It's at the very bottom of a chunk. I can't remember which chunk it is.
Oh, it's right there. I see it.
You find it?
Okay. Yeah.
What else we got, folks? Free for all now.
Are we gonna have to memorize like the color chart? Like,
No.
okay.
So if you need to answer a question that has to do with colored wavelengths, they would give you the chart. There was one, like the number 32 on your multiple choice, it gives you this chart and it corresponds with the colors. That's what they
Okay.
would do for you. Yeah. Tomorrow in class, we'll talk a little bit more about specifically what's gonna show up on the multiple choice versus the free response, and if there's anything else that you need to sort of go back and review. I will tell you right now that on the free response on Friday, you're going to need to remember how to find the average atomic mass, which is I think that's a unit 0 thing. So if you have multiple isotopes, how to find the average atomic mass.
I actually have a quick question from the packet.
Okay.
It's on page 6, and then I don't know if our pages match up, but it's example 15
Okay.
in part C. For the whole part C section, how did you know that it was a limiting reactant without showing any work?
You wouldn't be able to.
Wait, where's your work?
So in part 1, I did work. So I sort of cheated a little bit. If I see that I have 50 milliliters of 1 molar silver nitrate and I have 50 milliliters of 1 molar magnesium chloride, I can see that that's going to be the same number of moles of each. And I know from my balanced equation, which is way back at the beginning of that question, that I need 2 moles of silver nitrate to react with 1 mole of magnesium chloride. So I know that that magnesium chloride is going to be my limiting reactant.
Okay, so you still kind of need to show work pretty much. I don't know.
Yeah, you're still going to have to show something.
Okay.
So I just, instead of writing out the math, I said because of the mole ratio in the balanced equation, I can see that this guy is going to limit.
Okay. Thank you.
You could
Oh.
show out the two dueling stoichiometries to figure out which one's limiting also.
Oh yeah, I've seen it that way. Like, how do you do it like that with just taking the 2 without finding the?
To be totally honest, I normally don't do it that way because I think it's really confusing. I could totally change the answer key to have it show the other way. to have it show the two stoichiometries. I think that one is that way is a safer way, because I think when you do the comparison with the mole, sometimes you have the option to go, you think something should be bigger, but actually it should be smaller. And sometimes students make mistakes with the comparisons that way. But if you do the two stoichiometries, guaranteed you're gonna get the right answer.
Okay, thank you.
Yep. All right, we've got a couple more minutes left. I'll take questions or clarifications about anything.
Can we
Mhm.
go over number 22 on the multiple choice?
22. Yes, we can.
Like, I got the answer. I'm just getting confused on like the formula of sodium chloride.
Okay, so for this one, so sodium chloride, since
Okay.
since it's an ionic substance, we
Mhm.
want it to be with other polar things. Like ionic
Yeah.
is like the ultimate far end of polar.
Okay.
Um,
Got it.
and so A, C, D, and E are all polar
Yeah. I just
or have
got
hydrogen
messed
bonding.
up.
Yeah.
I got messed up when I tried to do the electron configuration for it.
Oh, yeah, no, because it's gonna be ionic, it's gonna be weird.
Yeah, that's what messed me up. Okay, thank you.
Yeah, yeah. Anything that you can see that has that sort of positive ion, negative ion thing in it, just
Mhm.
automatically assume it's as polar can be.
Got it. Thank you.
Yep.
I don't know if we already went over this, but on number 24 on the multiple choice, why is it A and not B?
Why is it A and not B? So A is showing two things that have hydrogen bonding available to them. So similar intermolecular forces are going to make things more soluble. And B, we've got water, which has got hydrogen bonding, but carbon tetrachloride is totally non-polar and doesn't have any hydrogen bonding in it.
Okay.
So this would be bad. It would not dissolve.
Okay. Got it. Heard.
For number 24, could you also like just look at it and see that like A is the only one that has two polar molecules, so they dissolve better than
Yep.
a polar and a non-polar? Okay.
Yep. Yeah,
Thank you.
because C and D have polars and non-polars.
Okay, thank
Yep.
you.
It looks like you already went over 25, but I missed it. So can you just explain why the answer is D?
So 25 is dealing with the ratio of the absorbance to the concentration. We should have a nice steady ratio because we should get a nice straight line if we graphed it. And so if you take a look at the ratios of the absorbance to the concentration, 4's ratio doesn't match what the other ones do. So that means 4 is off somehow. And it actually is that the absorbance is too low. That ratio is off because the absorbance is too low. Temperature has absolutely nothing to do with concentration or absorbance. B is, I don't normally say this, B is a stupid answer. because we're saying we're using a spectrophotometer. Why would you go and move to a different spectrophotometer for no reason? If the flow of light through the solution was restricted, that the absorbance should be higher, and it's actually too low. And so usually if we have mistakes with absorbance, it's because the concentration is not what we expect it to be.
Okay, thank you.
You're welcome. All right. Probably got time for one or two more quick questions. If anybody's got anything? Nothing? We good? All right. If you come up with anything between now and tomorrow in class, we'll have some time to ask things in class. Oh, Morgan, you got something?
Yes.
Okay.
Number 35. How do you know like which one to use the best?
Because we have a change in color, spectrophotometry is probably going to be the best. Spectrophotometry works really well when we have colored solutions.
Okay. How would you know if you use the solution? How would you know if you use paper chromatography for a solution?
So paper chromatography would be best if we have a mixture of things and we want to identify what's in the mixture.
Okay.
Gravimetric analysis would work if we are making a solid out of something. Titrations, we haven't really talked about titrations yet. That'd be for like reacting acids and bases together. The other type of filtration works if you have a solid already. And then what's the other one? Distillation would work. It's not on this list, but it's one of the other separation techniques. Distillation would work if we had two large samples that we wanted to be able to collect in the end out of a mixture. Usually they're both liquids. And especially this one says concentration. So anytime we're trying to figure out concentrations, spectrophotometry is probably the best idea. Remember, spectrophotometry is like what we did in lab today. That's what goes along with Beer's law.
Okay. Thank you.
You're welcome. All right, y'all. We are out of time. I'll see y'all tomorrow in class. Again, like I said, if you come up with anything that you didn't think of now or something comes up between now and then, we're going to be reviewing tomorrow in class. So that'll be a great time to ask questions. Everybody stay safe, stay healthy, and I will see y'all tomorrow.
Thank you.
Thank you.
Yep. Bye.
Thank you.
Have a good evening.
Have a good evening.
You too.